In today's lecture, we will discuss the problem of model checking, and I will talk about also Bayes factor, how to use Bayes factor for model checking. So if you recall, we discussed the problem that we have a data set. This is the data, and we wanted to see whether the data are coming from a given distribution. There are two things. One is whether we know whether the parameter value of the distribution is known or the parameter value of the distribution is unknown. So first thing, we wanted to check whether it is coming from Poisson distribution with mean parameter 2. And the second thing we checked is whether the data are coming from a Poisson distribution without specifying the mean parameter. And we discussed some classical methods, classical chi-square test, goodness of fit test. And then we talked about Bayesian posterior predictive p-value. And that posterior predictive p-value calculation for different statistics. We can choose different statistics such as mean, standard deviation, the number of zeros in the data set, because this is a count data, or the tail probability of that observed data distribution. And another thing, specifically for the Poisson distribution, we can check the relationship between variance and the expectation. So we know for a Poisson random variable, mean and variance are the same. So one thing to check is we can calculate the ratio of these two things. One is observed mean and observed variance, and see whether that ratio is too large or too small with respect to a predictive distribution. I did not give you all the details here, how you can do that, but this is some thought you can think of how you can do that checking. Thinking along the same way like we did for mean, standard deviation. So think about how you can use this information, the relationship between mean and variance, to check whether the observations are coming from a Poisson distribution. If the Poisson distribution is not valid, then alternative models can be considered, such as negative binomial model, zero inflated Poisson model, or this distribution called Conway-Maxwell Poisson distribution. We know that negative binomial model is a very flexible model for the count data. Why? Because it allows you to take into account larger variation than the mean value. But Conway-Maxwell distribution is more flexible than the negative binomial distribution because it allows larger variation than the mean and also smaller variation than the mean. Over dispersion and under dispersion are allowed under this model. So now consider this scenario. Suppose I'm interested in testing. This is a little bit different testing of hypothesis. Now I say I have two models, two possible models. One is lambda equal to 2. That means the data are coming from a Poisson distribution with lambda equal to 2. And the other model is the data are coming from a Poisson distribution, but without specifying lambda. It is not 2, it is something else. And between these two models, I want to choose the best model. How will I do that? So I will do that using Bayes factor. So let us calculate the Bayes factor and see what happens. So we have two models, two competing models. One where lambda equal to 2, and the other where I do not specify lambda equal to 2, but I say lambda is unknown, and we assume this prior distribution for lambda. So the Bayes factor is based on the marginal likelihood of the data. The marginal likelihood under null hypothesis is the probability that yi, observed value of yi, given lambda equal to 2, and if you write the probability mass function of the Poisson distribution and simplify a little bit, it turned out to be this expression, e to the power minus 2n, because you have n observations, 2 is the parameter, and 2 to the power s. What is this s? S is the sum of yi, sum the total of the observations, and you have 1 over the product of yi factorial. So this part is very easy under the null hypothesis because you have only one value of the parameter. Under the alternative hypothesis, things are more complex. So the marginal likelihood M1 is this joint probability, and you need to integrate out the parameter with respect to the prior density function. So we write down this expression, replacing 2 by lambda, and then we put gamma distribution. So putting that and doing the gamma integration, this is what we do, gamma integration. We get the following expression. Okay. Therefore, the Bayes factor in favor of the alternative is, we write the Bayes factor of the alternative model to the null model. Alternative model in the numerator, null model in the denominator is equal to this expression. And what do you want? If the data favors the alternative model, then the marginal likelihood under alternative model will be larger than the marginal likelihood under the null model. This is the intuition. But how large should it be? You can say 1, right? If it is larger than 1, then alternative model is preferred. But you have to think about the uncertainty in the data, right? Sampling variability in the data. So 1, that simple cutoff is not enough to say, yes, we are favoring the alternative model. Therefore, statisticians recommended that use 3 as the cutoff value. Obviously, there are ambiguities. Why 3? Why not 5? Like if you do the classical inference where p-value generally 0.05 cutoff value is used, but people may argue why 0.05, why not 0.01 or 0.1. Like same thing here in the Bayesian calculation. Bayes factor is used for testing, but the cutoff value is subject to some discussion, but generally 3 is used. So if it is larger than 3, then we say the data favors alternative model. And if it is smaller than 1 over 3, then data favors the null model. Question is, what if you have value between 1 and 3? If you have value between 1 and 3, you have some evidence, but it is not a very good evidence. So there is some room for ambiguity. Same thing. What happens if the value is between lower than 1, but larger than 1/3? Okay. So there is also room for ambiguity. Also, another thing is base factor. You see, M1, the marginal likelihood. Marginal likelihood depends on the prior distribution. So we assume gamma prior with parameter A and B. So it is sensitive to the prior choice. So if you have two distributions like the Poisson 2 and not Poisson, then you can calculate the base factor very easily. Here, it takes very simple form like b to the power a gamma s plus a. You can calculate it using your calculator, hand calculator, right? And see what happens for your data set. Now, let us talk about the negative binomial model. This is a very important model for the count data. So probability mass function for the negative binomial distribution with parameters, two parameters, mu and omega, is the following. So fx is the probability mass function, which is the probability that the random variable takes on little x is equal to this. And the possible values of the random variable are 0, 1, 2 up to infinity. Like the Poisson random variable, 0, 1, 2 up to infinity. And you may see different papers or online documents, they are using different forms of the negative binomial probability mass function. It can be presented through different parameterization. But this one is commonly used in the regression context and in the generalized linear model context. In the generalized linear model, what happens? Your response variable, we model how the response variable depends on a set of covariates. We have not talked up to that point, but this is our target to talk about the regression, where we allow the response variable or the outcome variable depend on a set of covariates. Then we use this form of the negative bias. And what are the interpretations? Mu, this parameter, E is the mean of the random variable, and variance, so this is the type, it should be variance of x is mu plus mu square over omega. Obviously, you see, the variance is larger than mu, right? It is mu square over omega. Omega. Here, omega is referred to as the shape parameter. As omega increases, the model reduces to the Poisson model. So if you allow omega to be infinity, then it turned out to be the Poisson model. The question is, is there any conjugate prior for mu and omega for this distribution? So apparently there is no conjugate prior for this distribution. This is very complex.
Like no closed form one or just
No closed form. No closed form, no conjugate prior based on our known distributions. So the point is, posterior sampling is very difficult. We have not talked about in this class yet that when, so you have two parameters, how do you sample it? One way to do it through Gibbs sampling, right? So conditional on omega, you sample mu, conditional on mu, you sample omega. But those conditional distributions are not simple, are not any standard distribution. So you need to employ some technique, sampling technique. So generally people use some kind of Metropolis Hastings algorithm, some kind of Metropolis Hastings algorithm to sample from this joint posterior distribution. You do not need to write the code, it is complex code, but some software are available to do the computation. And this is this package, BRMS package. But the solution is not foolproof solution. You will see it's very time consuming, number one. If you want to run this sampling, posterior sampling, it's very time consuming. And you may encounter convergence issue. So to run the code, what I do, so this is the data set. This is the function, BRM function. And the BRM function was written to handle the regression setup. Here, our response variable y, which is my data set, is regressed on an interceptor. Okay, so mu, essentially mu is written as follows. So in the regression, we model mu as exp of delta 0 plus delta 1 z1 delta p zp z1 z2 zp are p covariates, and y is the outcome variable. And what is mu? Mu is expectation of y. So in the regression setup, we model expected value of y given z1, z2, zp using this formula. So when there is no z1, z2, zp, we simply regress, simply write expectation of y is e to the power delta 0. So this is called the intercept. And in the code, it is written as y tilde 1. If we have z1, z2, zp, then we write y tilde z1 plus z2 plus zp, so on and so forth. We are fitting the negative binomial family. We specify it here, data equal to this, and this BRM function allows you to set a number of chains, number of MCMC chains. Why does it do multiple chains? Because it calculates the convergence, and in order to verify the convergence, they need multiple chains from different initial values. For every chain, the number of iterations I set equal to be 5,000, but you can set it to be a large number, generally 10,000 or 20,000 observations. I set it to be that small number so that it finishes quickly. It is a time-consuming thing. And these to save all the parameter values and other things. And you get the summary Okay, now let me show you what happens. In this code, I did not specify the prior distribution. So if you don't specify the prior distribution, the function takes its default prior for that delta 0 and the default prior for the shape parameter. What you see, the intercept term estimate is 0.81 and the credible interval, the lower limit of the 95% credible interval is 0.59 to 1.02. But other parameter, this is the shape parameter, came out to be this so large, okay, so large. So that means something is going not correct, okay. And I got some convergence comment. But what happened, because I said refresh equal to 0 or something, I did it so that you don't get to see all the warning comments and other things. But if you run the code without suppressing those comments, you'll be seeing the comments that there is a convergence issue and something else. And why is happening? Because the thing is, the likelihood function it does not have very sharp shape. It has kind of very flat shape. And it tries to maximize the likelihood somehow, or try to sample from that maximum part of the likelihood function. And the omega, the shape parameter, is very large. That is what you are getting, is very large. Remember, our data, I know, was generated from a Poisson distribution, mixture of Poisson distribution. But the two components of the mixture, they are quite close. So when you try to approximate it by a negative binomial distribution, naturally, your shape parameter will be large, and that is happening. So if you want to know what is the default prior or the prior distribution used for your computation, you can simply say this get prior, and it tells you that the prior for the intercept was student t with degrees of freedom 3. So student t is a very flat prior, remember, with degrees of freedom 3, very low degrees of freedom. And this is the center value, and this is the scale parameter. So it is not low variance prior. It has a very fat tail prior distribution, and inverse gamma prior for the shape parameter. So what I did next, we want to specify the prior distribution for the parameters. So I specified this prior distribution, normal prior with mean 0 and standard deviation 5, and gamma prior for the shape parameter as 2 is the shape of the gamma, and 0.1 as the scale parameter. And then ran the code, you see here prior equal to priors. And then I have very reasonable results. Reasonable results for the intercept term, the results are unchanged, more or less. It was 0.59, now it is 0.58, but the upper limit is 1.02, no problem. But the shape parameter is now in a much more reasonable scale. And you can see the comments here. Draws were sampled using sampling NURTS. So NURTS is an algorithm to sample from this posterior distribution. And people are still working on people are still doing great deal of research on the sampling algorithms. Okay, next, what I did. So this is a wonderful thing. We did it. But why did we do it? We wanted to calculate the base factor. Okay. We wanted to calculate base factor. For that, we need the marginal likelihood. Marginal likelihood under the negative binomial model. So this is the formula for the negative binomial. So marginal likelihood of negative binomial will be this guy. And then we took the prior normal prior for log of mu, right? So mu had delta in it. So mu, let me write mu in terms of delta. Okay. And you have and gamma prior for omega. The rate parameter was 0.1 omega. So it is 0.1 square gamma 2 d delta d omega 2 integration. Looks very nice looking, right? This is the marginal likelihood. You can imagine how difficult it is to do the computation of this thing just with two parameters. Just with two parameters. Anyhow, so we'll not do the computation analytical. We will not try to get the analytical expression of this likelihood. We will use the posterior samples to calculate this marginal likelihood. That is why we are first fitting the model, obtaining posterior samples from this model fitting. Now, before we do the posterior, if we calculate the marginal likelihood, few things I just want to do. One is, if you are interested to look at the trace plot of the intercept term, which is delta 0, or the trace plot of the shape parameter, you can do so using this code. So it gives you the density plot and the trace plot. Why do you need the trace plot? To check the convergence, right? Convergence of the chain. So it converts and you have 4 chains, chain 1, 2, 3, 4. And this is the density function. Density function, you can see the density function has the center is about 0.8, right? You can look at the scale on the horizontal axis. Next, for the shape parameter, the mode is around 25, and the shape parameter is a positive valued random variable. So the posterior distribution is right skewed, right? And also the trace plot gives you how it is converging. It is not excellent. The trace plot does not look excellent. You see, there are a lot of high jumps, right? High values and then low values. But overall, it is all right. Now, overall, it is all right. How do you know that? So there is one parameter, r hat. If r hat is very close to 1, that indicates there is a good convergence of the chain. Therefore, r hat is calculated if you have multiple chains. We have 4 chains to verify the convergence.
R hat is similar to R squared. Sense of
I cannot remember, but it is calculating the convergence of this one measure of calculating the convergence of the chain. What you can do, you look at the function, BRM function, put a question mark before the BRM function. It will tell you the description of how that R hat is calculated. Another thing, if you are interested, you can do ACA plot to see the dependence among the observations. For that, we can extract the MCMC output using the package called posterior. And this posterior, so if you write this, then it extracts the posterior samples. Using the posterior sample, I did not do it. You can do it. You can see that posterior draws underscore DF has the posterior sample for all the parameters. And you can play with those sample values. One other thing is when you play with these posterior draws, you will see the number of samples is much smaller than 5,000, not 5,000. It is 4 times 5,000. 4 chains, each chain is run 5,000 times. So it will be, you are supposed to get 20,000 posterior samples, but it will only show you about 10,000 posterior samples because half of the samples are removed as the burn-in sample. So the first half is removed. Okay, next is the marginal likelihood calculation. And for that, we'll be using this package called bridge sampling. And if you do that, then it results in what? Bridge sampling estimate of the log marginal likelihood is minus 70.37. Now, remember, this is our marginal likelihood actual definition. Calculation is very difficult. Therefore, it is estimated. using the posterior samples. Therefore, it says estimate. Look at this, estimate, not the actual marginal likelihood. What I wanted to compare now for this data set, the negative binomial model and the Poisson model. Okay, how do you do that? So I did already negative binomial. Let's fit the Poisson model. Again, using the BRM package, family equal to Poisson, and then repeat what you did already. And it gave you the log of marginal likelihood minus 60.78. The base factor of the Poisson model to the negative binomial model. Poisson model in the numerator, negative binomial model in the denominator. Okay. And the marginal likelihood. So that marginal likelihood ratio of the two marginal likelihoods came out to be 4.90. So 4.90, this is the marginal likelihood ratio of the marginal likelihood, keeping the Poisson model in the numerator and the negative binomial model in the denominator. And it is larger than 3, means the Poisson model is favored. If there is no strict rule that you have to keep the Poisson model in the numerator. You can keep the negative binomial model in the numerator. Then if the ratio is smaller than 1/3, then you favor the Poisson model. So whichever way, you keep it and interpret it accordingly. So here it came out to be 4.90. So we favor Poisson model over the negative binomial model. So the base factor is for comparing two models at a time. If you have multiple models, you do a lot of pairwise comparison, this versus this, or what you can do, you take, you consider the models which have the smallest marginal likelihoods and then compare among them. It's a very time-consuming task, calculation of the marginal likelihood. And people have written a lot of papers on how to estimate the marginal likelihood. For our problem, we have only 2 parameters. With that 2 parameters, things are very complex. Can you imagine if you have multiple parameters and you have it when you have many covariates in the model, then things are not simple at all, that calculation. We'll come to the base factor calculation in chapter, this is chapter 9, I believe. But anyhow, I just wanted to introduce you because model selection is very necessary for different model fittings. Another thing is the BIC, Bayesian information criteria. Now this BIC is produced whenever you fit a model, right? And it is equal to minus 2 times log of likelihood when theta equal to, the theta is the parameter, equal to its estimated value plus k times log n. And what is this k? K is the dimension of theta. This is Bayesian information criteria. And it is shown that BIC is approximately equal to 2 times log of the marginal likelihood. So that means it is minus 2 times probability of the data given a model. Okay, so if that is the case, then suppose I have two models. Let's say model 1 and model 2. I want to calculate the marginal likelihood of model 1 and marginal likelihood of model 2. So I can use then BIC to approximate the base factor. So base factor of model 1 to 2 is data given M1 divided by probability data given M2. Now this data given M1 is e to the power approximately e to the power what? 1/2 of BIC, right? BIC is approximately minus 2 times log of marginal likelihood. Then negative sign over there divided by 2 e to the power, yes, BIC of model 1, and down here it is minus 1/2 BIC of 2. So you get what? E to the power 1/2 BIC of 2 minus BIC of 1. So the base factor can be approximated then by BIC. Now let's do that. BIC calculation is very easy, BIC. Let's do that. But only thing is that we do not use any prior information. We do not use any prior. So this is our data. Let's copy. This is our data. Okay. We need library math. Okay. So first we'll fit the Poisson model. GLM and my data again follows 1 because there is no covariate in the data. So just simply write 1. Family equal to Poisson. That's it. Okay. And the other one is negative binomial. GLM NB. Yes. Data 1. That's it. GLM, look, okay, so this. So you see here, when you try to fit GLM, negative binomial, it has some convergence issue already. And you have seen that you got some indication when you try to fit the negative binomial model using the Bayesian setup with the very flexible prior. We avoided that using very informative prior distribution. So that means there are some inherent issues in the data that created convergence problem. So anyhow, so let's look at out P. It gives you the AIC value, right? And we can calculate BIC also. It calculates BIC value. And for negative binomial, it although there are some convergence issues, but it gave you the result. Okay, it gave you the result. It gave you the AIC value. Let us calculate the BIC value, 138, and base factor of Poisson model in the numerator, negative binomial in the denominator. Let us calculate that. It is it is 6.32. And it is, as I said, I'm keeping in the base factor calculation Poisson model in the numerator, negative binomial in the denominator. So it is larger than 3. So it is still favoring Poisson model over the negative binomial model. Okay. And the question is, this is an approximation of the actual base factor because these are not real marginal likelihood. Marginal likelihoods are approximated. Another comment is that here we are favoring Poisson model over negative binomial model does not mean Poisson model is the best model for this data because we compared only 2 models. Maybe if you fit another model, that would be better than Poisson model. So for comparison of 2 models, Poisson is the better. Questions? And I suggest that you guys get familiar with this package, BRM package. It is most useful among all the packages. First of all, Bayesian analysis is not easy. And why? Conceptually, it is very easy. It is not easy because the sampling part, posterior sampling is very difficult whenever we have multiple parameters and the model is not so simple looking. Beyond normal distribution, beyond Poisson distribution, things are not so simple. And this is one of the best packages out there. Using BRM package, you can fit different generalized linear models. Generalized linear models include Poisson, gamma, binomial, negative binomial. Lot of models are included within this generalized linear model. And so get familiar with this. It gives you whole lot of information. I have not used all of them and I have not read all the documentation. You read the documentation description, you'll know what information they are extracting from those posterior samples. They are very useful. And it is definitely handy in many cases. In many cases, we have generalized linear models, not beyond that. So for fitting that generalized linear model, you can easily use them. Also, the sampling step, you can manipulate the sampling step. They have a list of options of choosing different sampling algorithms. You can choose also. All right. Questions?